I guess we can start. Welcome everyone to part of the session on neural networks and artificial intelligence. And we have first half an hour talk by Cristina Masoller, who's an invited speaker. And please, Cristina, you can start.
Okay, thank you, Carlos. Let me go to full mode. Do you see my screen?
Yes.
Okay, so thank you for organizing this wonderful meeting in these very difficult circumstances, and thanks for giving me the opportunity to present this work here, and thanks for coming to this session. I would like you to please interrupt me anytime, because I cannot see the chat in my full screen, so I don't know whether you ask any question or not, but please feel free to interrupt whenever you want. The work I will present to you is entitled Combining Complex Networks and Machine Learning for Image Classification and Outlier Detection. This work was done by a PhD student, Pablo Amil, and several collaborators who I will show at the end of the presentation. So basically the idea is to use, as it says, complex networks and machine learning to classify images. And here you see an example. This is a retina image, and this is the network that we extract from this image. And for this network, we use analysis tools based on complex networks and machine learning to obtain some classification. So basically, do you see me? Yeah. My goal is to use complex networks and machine learning to classify this type of image. And this type of image is usually an indicator, or features extracted from these images are indicators of early diseases like glaucoma or diabetics. And it's also very important for person identification. And it can also be very interesting for alterations in the brain, because the retina is a non-invasive window to inspect the brain, and many diseases in the brain are due to alterations in the arterial system, and these alterations can also be reflected partially in the retina. So there is a lot of interest in trying to analyze this type of image, and to the best of my knowledge, networks have not yet been used. So it's a very interesting application. This is, for example, two examples of a healthy image and a diabetic image, and you can see there are differences, but the idea is to try to see how can we quantify them and with what reliability. So first we track the network, which means we need to segment the image and identify important sections in the image, and then try to compare different type of networks, and use, for this comparison, use machine learning algorithms to classify different types of pathologies or healthy eyes. So how can we compare the type of networks that we extract that have these characteristics? We have weight networks that are unweighted, no weights. They are undirected because we detect points and links, and also they have probably a different number of nodes. I want to show you again what is the type of network that we obtain. In the bifurcations, we have a node, and at the end, we have another node. I don't know if you can see them, but those are indicated with these little red points. So we have a different, depending on the image, we have different types of different number of nodes. You can see that it's a retina, it's a tree-like network. It starts in the optical nerve and goes diffuses along the eye. So how can we compare networks that have these characteristics, indirect, undirected, unweighted, and with different numbers of nodes? Well, it turns out that if you analyze the degree, the centrality, the assortativity, etc., these are informations that only partial information. They are really not by themselves sufficient to distinguish important characteristics of different networks. And this is mainly because not all the links have the same importance. And these measures do not take into account this fact. And here I have an example of 3 networks in which there's only a difference in one link. See, comparing the second network with the first one, we see that this link here is missing. while with the third one, there is a different link that is missing. Clearly, it's not the same if which link is missing, because in one case we have disconnected network, and in the other case, the network is basically connected except for just one node. So we need to have a measure to compare networks that take into account this issue that not all the links are equally important. So we have proposed a measure that is based in the node distance distribution of a node. This is a distribution associated to each node that takes into account the fraction of nodes that are connected, shorted paths, to node E with a certain distance R. So for example, this example is adapted from another paper. We have this type of network, and from one node, we see that we have 2 nodes at distance 1, 4 nodes at distance 2, and 3 nodes at distance 3. So we can construct a probability distribution, which is the node distance distribution of node E, which is this one shown here. So if I have a network with n nodes, it will be characterized by n distributions, a set of n distributions. And if 2 networks turns out to have the same set of distributions, they will have the same diameter, average path length, and so on. So how to summarize the information contained in all these distance distributions? We have proposed a magnitude that is called network node dispersion that quantifies the heterogeneity of all these distributions. And basically, we calculate the average distribution, and we calculate the Hilbert distance between each distribution and the average, and then we average these distances. So this is a magnitude that it characterizes for a given network how heterogeneous the distribution of links are. And then we can compare, using this measure, we can compare 2 different networks, G and G prime, but using this formula that it looks complicated, and in fact it is, because it tries to solve a problem that is not simple. But we have done extensive numerical experiments, and we have demonstrated that this formula gives a 0 only if the 2 networks are exactly the same, isomorphic. And it's also computationally efficient, and this allows to compare different networks with different numbers of nodes, because eventually we are comparing distributions and this node distance distribution. So let me show, to begin, a simple application of this formula, which is not related to images, but is related to the classification of brain signals, EEG signals. So we have analyzed 16 time series, which were recorded in a subset during 1 second, and we had freely available data, and from 107 subjects, 39 are control and 68 are alcoholic. And to apply this measure, first we need to transform each time series into a network, and then compare networks. So to obtain a network from a time series, we use what is called the horizontal visibility rule. This horizontal visibility rule is just a way to represent as a network a time series. It basically represents the points of the time series as these bars, and puts connections between points if there is horizontal visibility between them, as shown in this plot. So 2 points are connected if there's visibility between them, and in this way we obtain a graph that is unweighted and undirected, and it's also parameter free. So in this way, for each subset, we have 16 channels. So we obtain 16 networks, which are schematically represented here. And then from these 16 networks, we build a kind of super network by connecting different brain regions, different brain networks, if they are very similar. So the dissimilarity measure gives me how different they are, and if they are very similar, we put a strong connection. So this is, we obtain it in this way, we obtain the possibility of distinguishing between alcoholic and non-alcoholic subjects, because we identify 2 brain regions where the connection strength is higher in control than in alcoholic subjects. So we apply this measure to compare graphs, and now we're going to use it for classifying retina image. So first, as I said, we have to segment the image, and we obtain this type of plot where by using imaging processing tools, we transform this into a series of black and white and identify the pixels where there are segments and connected segments and endpoints, which are the nodes. And for that, we use an unsupervised segmentation algorithm that was adapted from an algorithm developed for cultural neuronal networks. So from images on neuronal networks, you can extract, using this algorithm, you can extract a graph, and we have adapted this algorithm for the retina images. And this is, again, is an example of an image that we extracted. And here you have, for example, a path with 4 steps from the blue 1, 2, and 3 links to the central optical nerve. So basically, I want to describe now the data that we analyzed: 15 healthy subjects, 15 glaucoma, and 15 diabetic retinopathy. And for each subject, we had the actual raw image and the manual segmentation, which was done by an expert. And also, we had the automated segmentation that we obtained from using the algorithm that I just described, that we adapted to the analysis of retina images. So we have 2 segmentations. One is done by an expert, and the other one was non-supervised. So this is a comparison. You can see that the automatic is not as good as the manual, and the results that I will present are much better for the manual because the segmentation algorithm is more precise. And we analyze it. For both of them, we analyze it. The segmented image, we analyzed the scalenoticized image, which is just the width of each pixel segment is reduced to 1 pixel, and the other one includes all the pixels, just technical details. And we also analyzed 2 additional databases with lower resolution. And again, if the resolution is not very good, our method doesn't work very well. The best results we obtained with the high resolution images and manual segmentation. So we defined weights for the links, which are related to the length and the width in terms of number of pixels, with some constants here to represent volume of surface or length. See, so we used length over area. That was the best. That was the weights that provided the best differentiation between the groups. And this is because for the type of pathology, we expected to have difference in this ratio of length over area. For glaucoma, the volume was the best, that performed the best, and that is because glaucoma is linked to an increase of intraocular pressure that perhaps modifies the volume of the vessels. So for each image, we calculate the fractal dimension in the 2 types of segmented images. We calculate the distribution of distances to the central node. We calculate the distribution of average weights along the path to the central node, the distribution of weighted degrees, and so on. And this is an example. You can see that from the analysis of the distribution, it's not that easy to differentiate the 3 cases. However, if we use, again, the Hensen-Shannon divergence to compare distributions, we obtain a vector, which is for each image, we obtain a vector depending on the distance between that image and all the others. And this vector of features is a vector that characterizes the image E. And then we apply the dimensionality reduction algorithm, which is known as ISOMAP. It's a very popular map algorithm for dimensionality reduction. And then we obtain from all these large vector of images, because we have, as I said, 15 times 3, 45 features, we reduce only 2 features. And that's what we plot in the map. And here you can see that we can, for example, using the distance distribution to the central node, we can separate healthy from not healthy subjects. There are some cases here that are mixed, but basically the healthy subjects are here and the non-healthy subsets are over there. We can use the mean weight distribution, again, along the shortest path to the central node, and this improves a bit the classification because it allows to separate a bit better diabetic, glaucoma, and healthy subjects. And again, if we use manual segmentation, we have a perfect separation. And in the automatic segmentation, which is the ideal case because we don't want an expert to have to mark every pixel, it's not realistic, but if we do it in an automatic way, the fractal dimension in this case is a feature that separates better the three cases. Also, the mean weight distribution is a good good measure to identify glaucoma and separates the blue patients from the other ones. Just to mention that the simple features do not differentiate. So for example, if we want to plot the number of nodes versus the numbers of links or the degree distributions inside that, we did not succeed in separating the three cases. So let me summarize briefly. We have used a measure to compare graphs which are unlabeled and undirected and have different number of nodes. We have used it for EEG classification and for retina fundus image analysis. How many minutes do I have? Do I have some extra time? No.
Well, we'll have like 12 minutes, including questions.
Brilliant.
So if you want some questions,
yeah.
Maybe 7 minutes.
Yeah. And the last few minutes, I want to show you the second method that we have used for image analysis. This is again retina image, ophthalmic images, but it's a different type of images from Institute of Microcirugía Ocular in Barcelona, and it's used for the diagnosis of glaucoma. And you can see here that it can be classified in 4 categories: closed here, narrow, wide, and wide open. And we want to compare many images, again, to differentiate glaucoma or to identify patients with an early signature of glaucoma. And we want to use a distance to compare pairs of images which are is appropriated. For example, we want images that are similar to have a small distance, images that are not so similar, medium distance, and here images that are very different to have a large distance. So we have applied this idea of comparing in the same way as before images with different distances, and then again applying isomap to obtain 2 features, and then plotting these 2 features in a plane. So basically it's the same procedure as before, but using a different type of distance metrics. And you can see here that the algorithm succeeds in plotting in the red corner the images that are very close angle, and putting over on the other side the images that have a wide open angle. And actually there is a very good correlation between the results obtained by automatic features, which are the features of the nonlinear dimensionality reduction algorithm, and the features that are given by a doctor that measured or estimated the mean angle. So we obtain a really nice correlation, meaning the small angle is in one corner and large angle is in the other corner. But the question is, can we do better and can we improve this correlation if we decide to try to remove images with artifacts? As we know, that in biomedical imaging techniques, there are often many artifacts that are really detrimental for the results of the test. And if we can identify in an automatic way which images have artifacts, we can remove them from the training test. So I'm going to go to the last part of my talk, which is how to identify outliers. And what is an outlier? From a practical point of view, I think we all have an intuition of what an outlier is, but from a practical point of view, an outlier is something that when removed from the training set the performance of a machine learning algorithm improves if I remove outlier data from my training data. So basically, we're going to propose two methods. I don't know if I have time for the second method, but at least I will explain the first one for outlier detection. So again, we end up with a set of features that identifies an item of the data set. For example, for an image, we have as a set of features is the distance with all the other images. And then we can define distance between two items from how different these vectors of features are. So the first method is based on using what is called network percolation. We have a set of nodes. They are, for example, in this case, there are all the images I have. I connect them with certain distances between them. So two images, if they are very similar, will be very close and will have a small distance. And two images that are very different will have a large distance. And then what I do is start removing the links that are very long. So for example, here we see that the image number 24 is the first one to be out of the cluster. And then is image 11 is also out of the cluster. This is because the distance between 24 and all the rest are very, very large. And also the distances between 11 and the rest are very, very far. So these ones is a way to identify outliers. I obtain an order in which the elements become disconnected from the giant component, and the first ones that become disconnected are the ones that are more different from all the other elements, because the links are the distance defined by the metric that I showed you before, by this distance here. So each element has a vector of features. I compare them by using, for example, this distance, which is a modification of Euler distance. And then we can identify the outliers by removing the links that are longer and seeing which elements become disconnected. Well, we have tested this. Important thing is that this is completely parameter free. I don't have to specify anything except for the distance. I have to give a proper distance to compare elements on the data set. And I'm not going very fast. I don't have time to explain the second method. This takes a lot of time, but I want you to know that we compare different methods for outlier detections. We have proposed this percolation that I just explained to you. We have also proposed another one that is called isomap, or based in isomap, and then compare with other methods. And here you see the images that have been detected as outliers by the different methods, and they are because they have artifacts, or they are very black, or they have some things that make them look different from the other images of the data set. So once we have removed these images from the data set, we see that at a certain point, the correlation between the features obtained by the algorithms and the features given by the expert doctor improve. And that's essentially the demonstration that we are removing outliers, because once we remove the outliers, we improve the performance of our unsupervised algorithm. And the way to quantify this improvement of performance is obtaining a better correlation between the results of unsupervised algorithm and the results given by a doctor. The correlation improves when we remove that type of image. If we remove random images without pre-selecting outliers, we don't get any significant correlation, improve in the correlation. The correlation is below 0.8 and remains below 0.8, while by cleaning the training data set using our algorithms, we obtain a significant performance. Well, I'm concluding by saying that we have used this also to a method to identify outliers in a data set with faces, and we have put some extra things in you can see here some artifacts in the images, and we have verified that the algorithms really perfectly detect the images that have outliers. And well, we have been able to quantify the performance, and we have also used a freely available credit card transaction database to identify frauds. And basically the algorithm performance is similar compared to the other algorithms that have been performed in the literature. So these are the two methods that we have proposed. We have compared with 3 other approaches to outlier detection, and we have used the OCT, the image database, the ophthalmic image database. We have used the face database and the credit card transactions, and they work very well. It's a very generic algorithm because it's only based on defining the distance between elements in the database. So to summarize, the second conclusion is that the performance of the outlier detection methods depends, of course, on the data, but the ones that we have proposed are competitive in comparison to other methods. The big advantage of the percolation method is that parameter-free. I didn't have time to explain the other method, but it has 2 parameters that when we set them properly, we can outperform any of the other methods that we have compared. But these 2 parameters have to be really set properly, and they are really suitable for high dimensional databases that are not too large. So the elements of the database are high dimensional, like images, but the database cannot be too large because the execution time grows linearly with the dimension of the data, and at least as n times cells the size of the database. So I want to finish by thanking my collaborators, people working in IMO Barcelona. This work has been done in collaboration with Ulrich Farlis, Fabián Reyes, and Led Guzmán Vargas in Mexico, Irene Sandiñas Nadal in Madrid, and Nahuel Almeida in Córdoba, Argentina. Thank you for your attention.
Thank you very much, Cristina. We have three minutes for questions. If anyone would like to take the microphone? I was wondering, Cristina, if I understood properly, rather than trying to beat the experts with some machine learning algorithms, your goal was rather to improve the diagnostics of experts, right?
No, basically, yes, it's improve the diagnostic, but try to do it unsupervised. So in a way, it would be developing algorithms that can be executed with as a pre-analysis, and then if we detect signatures that there is some early disease, then the patient can go to a proper doctor to see what's going on. So basically, we don't want to substitute or replace the doctor, but we want to say that if somebody goes for a routine analysis, this type of algorithms can be incorporated in the instruments that take these images, and they can provide some warning whether this person is likely to have some signature of a disease.
Yes, I think yours is a nice example of the capabilities and benefits of machine learning, in the sense that it's not replacing humans, it's let's say augmenting or making it cheaper, so that with your method you can monitor millions of people relatively cheap, and then those who need further assistance, those are guided to humans.
Exactly.
So it's improving what we have already, not replacing it with something different.
Yeah.
Okay.
I don't know how to stop sharing my screen. Do you know how to? Can I stop sharing? Are you still seeing my screen or not more?
Yes. Yes.
I don't know how to go out.
There's like a button.
Oh, I don't know. I think I'm gonna have to go out and come back to the meeting, because yes, I don't know how to stop. I cannot see it. You see my screen, so I don't really know where to go.
I think I stopped it. Yeah.
Okay.
Now
okay.
it stopped, so it's fine.
Yeah. Okay.
Okay, so next speaker is Juan Luis Cabrera. Would you like to share your screen?
Hi, Carlos.
Hello.
Hello. Can you listen to me?
Yes.
Good. So I'm going to, this is a record talk. So this is the one.
We could see your screen, but we couldn't hear it. And
Hello. So I have some problem here with the sound. So
yes.
let me see if I can do it. Diffusive movement is characterized by a hard exponent in the mean square displacement larger than 1/2. We have a Lévy flight superdiffusion of organisms was predicted in 1986. It can be also.
I think we can hear it now, or it's intermittent.
So sorry, is it working?
I could hear some of the audio, but it was intermittent, at least on my side.
Why? Let me see what's happening here.
I couldn't hear the audio.
Okay, I'm going to start again, right?
Yes.
Okay. So now, share.
Yes, we can see your screen.
Producing foraging trajectories done with
Esther
describes super-diffusive Lévy flight. A super-diffusive movement is characterized by a hard exponent in the mean square displacement larger than 1/2. We have a Lévy flight super-diffusive movement when it follows a rise by an exponent with a value between 1 and 3. Superdiffusion of organisms was predicted in 1986. It can be also observed in other non-related like human stick valence, where the fingertip shows superdiffusion. When this work was published, it was not clear if superdiffusive movement in animals had an intrinsic origin. That was established recently in 2019, studying Drosophila larvae. We would like to advance an hypothesis about the neurological basis for Lévy's superdiffusive movement. This hypothesis is based in wireless competition. It has been proposed as a paradigm for neural information processing. It can be found in Lotka-Volterra or May-Leonard system. Here we show the case of a Lotka-Volterra discrete map. We have shown the necessary and sufficient condition for the appearance of wireless competition. In such a state, the system shows an heteroclinic orbit in the phase space. The circulation goes through the fixed point of the system and remaining at a small time in those fixed points. In particular, we have been able to describe how is the time spent around each of those saddles. How are the residence times? Determining the residence times is very easy because it is just the width of each peak observed in the temporal series. We advance the idea that those residence times contain information. Here we show results of a 6-dimensional Lotka-Volterra map. We can see the temporal series of each of the components have the typical alternance of the signals, where none of the components dominates of the other while they are continually competing. We can determine the residence time around a saddle. See there at step 1. We're going to show you a procedure to extract information from this temporal series. So determining the residence time is just calculating the difference between the time entering in the saddle and the time getting out of the saddle. That time is just the width of a peak. With such a width, we have a small delta at the step 1. So we can, from a set of this difference, establish a series of residence times, as is explicit at point 2. In fact, that a series of residence times is shown in the upper panel with the letter B, where that series is a very fluctuating one. From using that temporal series, we can calculate the difference between residence times of the visit K and a visit K plus certain temporal distance, capital D, to the same saddle. And we have now an additional temporal series called here Greek delta, which is displayed at the panel C. With this temporal series, we built a scheme which is just assembling all of these capital Greek deltas to have a new temporal series as the one shown in the panel C. We can also propose a second scheme to produce large set. In this case, the capital Greek delta is calculated as in the scheme 1, but now include all the activation peaks as at step 5. An important aspect to note is that we are working with a dynamical system that has a dependence on a control parameter, which is R there in the Lotka-Volterra. That means that when we calculate the evolution of the system in the regime of wireless competition, we can change that control parameter, obtaining different competing behavior. From those temporal series, we are able to build new temporal series following scheme 1 and scheme 2, and we can calculate the power spectra of those temporal series for the different values of the control parameter. A representation of a power spectrum for different values of the control parameter can be seen there. The one at the left is calculated for a range of values of the control parameter, and the one at the right is assumed inside that structure. To have an idea what's going on there, we represent on a plane those values of the frequency and the control parameter where the power spectra is 0. Those values are represented there as black points on a yellow background. The results obtained with the scheme 1, which is at the top panel, and the one obtained using the scheme 2 is the one shown in the lower panel. It is obvious that there is an intricate distribution of frequency values satisfying that condition. We carry out a multifractal analysis for both schemes, and the result can be seen on this plot. Here, the singularity spectrum obtained using the black points for both the scheme 1 and the scheme 2 shows the expected singularity spectrum for a multifractal, and that the yellow points do not show such singularity spectrum as a spectral fractal. So with this information we extract a fractal dust. That is, we can fix a value of the control parameter R and take a line of points. That line of points for fixed value of R is the set of points in the right figure, where a set of points are points coming from the power spectrum. That object is a fractal object with a fractal dimension 0.841. So from that fractal dust we can induce a superdiffusive two-dimensional random walk. How? Well, first calculating the distance between two successive points that we call df, and with that value we can produce coordinates x and y on the plane and assign angular deviation coming from a uniform distribution in an interval 0 to 2p. So the sets of points in the fractal dust, after being submitted to that calculation, are able to produce a random walk on the plane, and when we have that random walk we can determine the mean square displacement by direct determination, just by calculating the best fit, or using the generalized H method proposed by Di Matteo. We obtained that for the case of the fractal dust inducing a random walk, what we obtain is that the Hurst exponent is larger than 1/2. That means that we are in the case of a superdiffusive random walk. So we use data from the collaborative research in computational neuroscience data sharing repository, and in particular data from non-Evans rats during an open field task in which the animal chased randomly placed drops of water or pieces of Fruit Loop. So using this temporal data we were able to decode also Lévy walks from these experimental data. This is quite large set. It's around 180 gigabytes of information when compressed. You can see here in the plot A the temporal series and a certain threshold that was used to determine the width of the spikes. From there the capital Greek V at the plot V, and at the plot C an example of the power spectra. From these power spectra we were able to calculate a fractal dust shown there at D on that yellow background. From that fractal dust we were able to determine a two-dimensional random walk whose mean square displacement behave as shown at the plot F, and it shows a Hurst exponent with a value 0.942, which is larger than 1/2. Also, when the distribution of steps is calculated, we can see at plot G that it follows a power law with a negative exponent nu, whose positive value is around 1.301, which is between 1 and 3. That means that from the lone Evans rats we are able to obtain a superdiffusive Lévy walk from its neurological recording. That means that from the hypothesis of the heteroclinic circulations based on the winnerless competition dynamics and the resident times spent on the saddles, we can infer a superdiffusive Lévy walk. So what else can we do with these schemes? Can we obtain something similar for other kind of model data? To answer that question, we also analyze additional data. This case is an experiment of a voluntary movement in mice. This is a smaller set, and as you can see here, the raw data, an example of that raw data is at the plot A, and from that temporal series, the capital Greek delta temporal series is shown at V, and the power spectra is shown at C. On that power spectra, we can calculate fractal dust, which has a fractal dimension of 0.6 or 3, and from that fractal dust, we can build a random walk on the plane that has a mean square displacement behavior characterized by a Hurst exponent 0.702, also larger than a half. But the distribution of steps doesn't show a power law. We don't have enough data, and so we can only say that we have a super-diffusive walk, but not obtained the Lévy walk. We're right to the conclusion. We think that it is possible to explain interesting complex dynamics based on underlying instabilities, as is the case of the heterocline circulations in the wireless competition. That such complex dynamics is functionally relevant. In this case, is the one that is responsible for the super-diffusive Lévy movement. We showed that the wireless competition produced heteroclinic orbits, and from then a multifractal coding procedure that allows to explain the observed Lévy search patterns in animal at the neurological levels.
Okay.
Thank you very much.
Any question?
I have a question. I was wondering, from what I've known about foraging patterns that can be approximated with Lévy flights, in some cases they depend on the distribution of the resources, in the sense that if animals had an environment where resources are homogeneously distributed, which I don't think it's natural, but anyway, it's in an artificial environment where resources are homogeneously spread, then it wouldn't be as advantageous to have a Lévy flight strategy. That it makes more sense in real environments that have a heterogeneous distribution of resources. But then the precise exponent of the distribution of resources, it might or might not affect the exponent of the Lévy flight side. I don't know whether this is the case, because I understand this is just a hypothesis. I don't know whether it's the environment that triggers this search strategy or the other way around, that the environments end up having such distribution because of the search patterns.
Yes. So that's what that was the problem established between what is called the intrinsic and the extrinsic hypothesis, and that I try to specify that in one of the slides. That was already solved. There is not an extrinsic reason for super-diffusive movement in animals. It's an intrinsic reason. That was already a proof in this paper recently in last year. Let me tell you which one. It's the one by Swift and is here. Let me tell you the reference is yes, a group of Sims and Bernie. It's published in eLife. There they studied the case of larva, Drosophila larva, and they manipulate the Drosophila larva, and they took out the central pattern generator, and they showed that even so, the larva is able to follow the super-diffusive movement. So it is already established that there is not an extrinsic reason to producing that kind of behavior, if intrinsic. So our work was before that. We
Yes.
were searching for a neurological origin a couple of years before that, and it's the only detailed approach still. Obviously, there will come much more ones, probably.
Mm-hmm. Yep, very interesting. Is Axel Hutt here? Because I don't see his name, but it might be that there's another name on his account.
Okay, so there's no more questions.
Well, I don't see the other speakers, so if we have some time, if there's any other question for Cristina or for Juan Luis, we can take advantage or move on to the gather.
Well, maybe a remark. Oh, maybe a
Yes,
remark. I don't know if you know this type of research, but there's also Lévy flight patterns in human memory recall, which is very interesting. So if you ask,
yes,
yeah.
I have read something about that. I don't have a clear vision of that research, but yes, I know that paper, right?
So
very superficially.
Yeah. Okay. Well, yeah. I was going to ask. So maybe, do you have an idea what the connection is between those two types of search? Because it's they call it kind of a search strategy.
Yes, I mean, both are in some obviously based on neuron dynamics, right?
Yeah.
So in this case, our hypothesis was that neuron dynamics is based on specific unstable dynamics.
Right.
The one of wireless. So memory management, who knows what's the dynamics involved in memory management, but obviously it's a neuronal one.
Yeah.
So if the one driving neuron dynamics is this kind of wireless competition one, where we shall expect that type of super-diffusive movement.
Yeah.
In fact, we were inspired by a very different experiment, which is the one of stick balancing.
Right.
It's a control experiment. So the fingertip was describing that super-diffusive movement. So in fact, what happened is that the fingertip is trying to track the top of the stick. So it's also a type of search.
Yeah.
So that's where the first connection came from. So, but the stick balance is an unstable system. So the next step was to try to find an unstable dynamics that you may fit inside a neurological context. So we have no time to exhibit results from additional analysis. For example, conductance models, which are neurologically plausible, because obviously a Lotka-Volterra map is not something meaningful in a neurological context. But in our paper, there is also information about the application of the same approach to conductance models. You can extract also a fractal dust from there, and you can also produce that super-diffusive Lévy movement. So, well, we know that we can use that conductance models, which they are meaningful in a neurological context. So the question is open whether we can reach from there to more higher order functions, neural functions.
Interesting. Thank you.
Thanks a lot.
Yeah. Axel is here. He had some computer problems, but Axel, would Do you have a presentation to share your screen?
Okay, thank you.
So
Nice.
sorry for being late. So I guess I have a few minutes left. So let me see whether this works. So can you see my slide?
Yes.
Okay. So I wanted to say something about additive noise and how it changes the topology of neural networks. And there are several aspects. And so first I would like to introduce the idea by a recent study, how this affects the brain and how this describes coherent resonance in neural networks. And so in the brain, you have a driving system that sets the level of excitation of the brain. And this is the ARAS ascending reticular arousal system. And we started with a neural activity model where we have three areas. It's the cortex, the thalamus, LGN, and RTN. And we drive these three areas by additive noise and just studied what is the behavior and how does the cortical dynamics evolve and change with changing input. And so we did this, and these are the differential equations. So these are stochastic delay differential equations. They are for the different areas, and we have in total for each area we have 500 nodes. So we did numerical simulations of these. And as I said, you have driving noise, delay, and nonlinearity. There's several features in there, but the major part is the noise, the additive noise. And at the end, we determine the EEG. This is the dynamics of the cortex. And these are experimental data. And here you see that the white line shows a peak of power. This is frequency and time in two subjects. This is experimental data. And you see that there's a strong frequency at 10 after some time at 10 Hertz. And when we do our simulations, we find the same. So, and we get this by reducing the noise in the brain. So we analyzed the spiking activity in the brain, so of the single neurons, and we've seen that this changes, behavior changes dramatically in different areas. And we see that each area is synchronized, becomes synchronized when you reduce the noise. And before it was asynchronous, and with reduced noise, it's synchronous. And also the areas, the synchronization between areas breaks down. So the areas are not synchronized anymore. So before, in the beginning with high noise level, they are synchronized, and we reduce the noise, then they are desynchronized. So at the end, we have a fragmentation of the brain by additive noise. And mathematically, we tried to understand this behavior, and we came up with a reduced model. These are now only 4 equations with 4 equations for each node. And we made a mean field approximation. I give it like this, and the additive noise is still there. And then at the end, we can show that the additive noise changes the transfer function, the nonlinear interaction in the network. And at the end, what we find is a Hopf bifurcation. So what is going on when we decrease the random noise level? So we get a Hopf bifurcation. So additive noise induces a Hopf bifurcation in the system. These are the solutions. So from top to bottom, in the top row, you have large noise level, low row, you have low noise level. And so you see the frequency changes, and we can describe this analytically, how this changes. In the second model, we dealt with coherence resonance. So what is the model here? We have a network of excitatory and inhibitory neurons. We have self-connections, and we drive this by noise. And then these are the equations. And here you have the uncorrelated noise. And yeah, they uncorrelated in space and time. we have a network that is the Shreni network with a high connectivity probability, but that's not that important. So we can reduce this connection probability quite well. And when we do simulations, then we find the following. So this is the spatial temporal activity of the field. And now we increase with time the noise level. So we increase the noise level, and you see it fluctuates at a certain level. And after some time, it drops down to a lower level. And this drop down is exactly what we see. And when we take a look at the power spectrum, then we see coherence resonance. So this is the mean field dynamics. So we compute the mean field. These are V bar and W bar. And in addition, we have fluctuations around about these mean fields. And these follow an Ornstein-Uhlenbeck process. So we found this. And at the end, we can describe analytically what's going on. And at the end, the transfer function that we have here, again, is shaped by the additive noise. So at the end, what we see is that for low noise level, we have flat or no peak, no oscillatory peak in the power spectrum. But for high noise level, we have a strong peak in the mean field, and we have a strong coherence, phase coherence. So at the end, you can explain this like this. If you decrease the noise, you jump from equilibrium, a stable node, to a stable focus. So you do a phase transition by increasing the additive noise, and there you jump to a bottom branch of this bistability where you have oscillations. And this is coherence resonance. So here we have the results at the power spectra in a simulation with from top to bottom with decreasing noise with increasing noise level, and then we came up with a partially linear theory, so we can compute the power spectrum, the analytical power spectrum of this, and at the end we find very similar, it agrees quite well to the simulations, and this is exactly what happens in coherence resonance. You increase the noise, then you induce a certain frequency. This is this peak here at 0.5, it emerges at 0.5, and then it vanishes again. And this is coherence resonance. So at the end, taking things short, so we've shown that that additive noise induces a frequency shift of EEG, so it can move the frequency of a system. It induces a fragmentation, so that the areas in the brain decorrelate. And in addition, it induces oscillatory mean field activity, what is a sign here of coherence resonance. So, and what we want to do is we apply this currently to general anesthesia, what I've shown. Currently, we work on eyes open, eyes closed conditions. So what's going on there with how is the alpha activity generated? This might be an effect of coherence resonance, and we work on schizophrenia. In addition, from a mathematical point of view, we would like to study other network topologies beside the Erdős-Srény network, for instance, scale-free networks. So thank you for your attention.
Thank you, Axel. I have a quick question. Would you consider additive noise as a type of antifragility?
Pardon?
Would you consider additive noise as a type of antifragility? If I don't know whether you are familiar with the concept.
No, what do you mean by this?
Well, it was proposed a few years ago by Nassim Taleb in economics, but applied to different areas, and it's basically a word that characterizes systems that benefit from noise or thrive from noise.
Okay.
So
sorry, but can you write me this in the chat? Then I can look it up. It sounds interesting because
sure.
My work is around the effect of additive noise, and so I work on that for 10 years now, and I'm really curious about all additive noise effects. So maybe
yes. So I think it might be related.
Yeah. Okay.
Juan Luis posts in the chat. Axel, please post a link to a preprint if you have it.
Yes, I have a question. I'm not sure if I'm following you. You said also that that noise was Orsen-Uleve correlated, right?
Yes, uncorrelated, yes.
Uncorrelated.
Uncorrelated, yes.
Okay, so, sorry. Thank you.
Yes.
So, that's all.
No. So that's a difference, you know, it's just noise. So it's not correlated, it's independent of the dynamics, it's not multiplicative, it's just additive noise. But the key idea is that I can summarize this quickly. The key idea is that by the nonlinear coupling in the system, this additive noise becomes multiplicative noise. So the effect is again multiplicative noise, what is well known to change a system. So by the nonlinear interaction, by certain nonlinear interactions, you get this effect. That's the reason why you have it.
Okay, thanks.
Okay. Well, thank you very much, Axel, and all the speakers of the session. We have now 23 minutes left of the break. If you want to go to gather town to one of the sessions, or also take a quick break. And afterwards, there's the keynote lecture by Scott Kelso on the main room. Thank you all.
Thank you.
Thank you.
Thank you.